Okay, welcome. We're doing we're going to calculus AB, and we're going to start off with limits. Much of the limits sections that you guys probably have covered already was in pre-calculus. It is part of the pre-calculus coursework to go through limits, but we're going to go over it again. And so this first section should be pretty easy for you guys. But let's go over and talk about what limits are and why we need them. Okay, limits in calculus, the idea is, depending however your teacher wants to teach it, I say, what should it look like? Like, what should it have looked like? It might not be there, but what should it have looked like? Now, a dumb example is the limit as x approaches 2 of x minus 2 over x minus 2 and x plus 1. Now, this problem, can I actually say x can be 2? Now, in Algebra 1, we just simply plug in the number. And if I plug in the number, we end up with 2 minus 2 over 2 minus 2 and 2 plus 1. And we realize we have a fault here. Because 2 minus 2 is 0, so we end up getting 0 divided by 0. And that doesn't make any sense. We learned that 0 divided by 0, or 0, is not an answer. So this actually leads us to a special term, and this is called indeterminate. 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 Did I misspell that again? Indeterminate. There it goes. Indeterminate. And this fancy word, indeterminate, if you break it up in English, it means you can't determine it. It's just the word in with the word determinate. It means you can't determine it. And that's actually what our problem is. Because it's 0 over 0, it doesn't tell us any information that's useful to us. So what the hell? So it turns out, just like in pre-calc, that, hey, doesn't x minus 2 and x minus 2, whatever they would be, don't they cancel out? Couldn't we say they cancel out? And we could rewrite the problem as the limit as x approaches 2 is x plus 1. And if I go ahead and now plug in 2 now, this would be 2 plus 1 is equal to 3. Now, this isn't what the value really is. This is what the value looks like. Now, I'm going to pull up our browser in just a moment. So we look here and we're asking ourselves, so you just told me, Mr. Ko, that there isn't an answer, and then yet you gave me an answer. Like what's the answer? And here is our previous and our current thought mixed together. If I had wrote f of 2 of x, darn it, I'm not sure what that one. Oh, yeah, there you go. Of x minus 2 yeah, by plugging in 2 here, we would end up with indeterminate. But when I write it as a limit, it's not what is it, not what it is. This is an is. This is what should it have looked like. And that's the big difference. Now, I'm going to graph this on Desmos for you guys. Give me one moment. Okay, let me share the screen. I'm going to stop sharing here. So if we look here, this is the graph of the equation. And we said when x equal to 2, so let's go ahead and zoom in at 2. So what does the graph look like when x is equal to 2? The graph looks like, when x is 2, the graph looks like 3, right? Everyone see that? But can you guys actually see the hole there? I'm gonna zoom in really in. You guys see the hole? See the hole? You see it yet? I see it. Only smart people see it. You guys see the hole? The point is that the graph doesn't exist at 2. But by you saying it doesn't exist, it doesn't tell me information. I need to know an answer. When your parents ask you a question, what are you doing this weekend? But don't you have an idea? You have an idea. I'm just not telling my parents. The idea of a limit is not what is it, but what should it have looked like. And in this case, it's not undefined. It should have looked like 3. On the right side, it looks like 3.07, 3.6, 3.5. The right side looks like 3. The left side, 2.9, 2.99, 2.99999, 2.999999999. This looks like 3. Both sides agree that this should be 3. And that's the goal of a limit. That not only the left side and the right side agree, that the left side and the right side agree that this should be 3. Okay. So this takes us to what is the idea of a limit. The idea of a limit is our goal. Here's the overall goal of a limit. Not what it is, because it was not useful to me. It was indeterminate, it was undefined, and that doesn't tell me enough information. Well, let's find another way of solving it. It turns out we could have simplified the problem, and by dividing the x minus 2 out, we were able to say, hey, this value should look like 3. Now, a big deal for us, a couple things we want to take as characteristics. So our graph kind of look like this. Here's our 2, and here's our 3. For a limit to be true, we have a couple conditions. So one of the conditions is that the left and the right limit have to agree. Now, how do we write this idea of left and right limit? Well, we already wrote limit. So the limit as x approaches 2 from the left side, and the limit as x approaches 2 from the right side. And we'll write that equation again, x minus 2, x plus 1, x minus 2, and x minus 2, x plus 1, x minus 2. That's ugly. Okay. So the terms here, math people are all about efficiency. And if I could write a notation rather than writing it out in words, 100% I'm going to do it. Remember sine, cosine, tangent? Instead of writing sine out, we just wrote sin. Instead of writing cosine out, we just write cos. Instead of writing the word addition, we just use a plus sign. It's all about reading the language of math. And for us, if you guys all notice the little plus and minus sign, is that this refers to the left side. And this is the right side. So from the left side of my equation, here, I see that, well, the graph looks like it's approaching 3. See, it's approaching 3. So I can write, it looks like it's going to be 3. On the right side, coming down, that was 3.01, right? According to Desmos. 3.01, 3.001, 3.0001. It's going to look like 3. So this fancy definition of writing a limit is that the limit as x approaches, let's say the letter C of f of x is equal to the limit as x approaches C from the left, as well as the limit as x approaches C from the right. If the limit is true, that means the left and the right limit must also exist because they're all leading to the same place. We have another way of writing this, a fancier way, but this is the general idea. If we said the limit was 3, that means the left and the right side had to be 3 also. But what if we spun this around? What if I said the left limit as x approaches, let's give ourselves another example, 5 of f of x was 4, and the limit as x approaches 5 of f of x was 3 from the left and the right. So if you notice, I put those little tiny little marks for left and right. Let's draw ourselves an example here. Here's 5 and 3 and 4. So from the right side, we're approaching it from the right. That looks like 3. From the left, it's 4. Could you then tell me that there's a value we could say it looks like? Could we say the limit exists? Okay, this is just a general idea here. Can we say the limit even exists? Remember, the limit is what should it look like? Now, let me give you a side story, and it's about 3 monks. So 3 monks were trying to describe an object. Okay, they're trying to describe an elephant. And if we saw an elephant, we would say a big flappy ears, big feet, funny looking tail, and a nose that can shoot water. But these monks were blind. 3 blind monks. The first monk tries to describe the elephant as, an elephant is like a tree. Okay. The second elephant tries to describe the elephant as, the elephant is like a wet hose. And the third blind monk said, the elephant, no. The elephant is like a rope. Are these monks wrong in any way? No. To their own perspective, they are not wrong. But do they have an overall consensus of what the elephant looks like? No, they do not have a limit. So unlike what we have here, the left side said 3, the right side said 3, the limit must be 3. Yes, we have a consensus. That's what it looks like. Over here, if the left was 4 and the right was 3, there's no consensus. The answer here is no limit. And that's perfectly fine. Not everything has a limit. So we can say no limit if we can agree that there is no answer that everyone kind of falls to. So these ideal limits are not really like solution. This is what it is. It's more like us trying to find a way to continue the conversation. What should it look like? Let's go ahead and look at another way we use limits, is this question here. What is the limit as x goes to infinity of the equation 1 over x? Now, if you guys remember how to graph the graph 1 over x, this is what we call a rational graph. We have a vertical asymptote. Does anybody remember? Just don't need to say it, but does anybody remember what the vertical asymptote for this graph would be? It was a long time ago, Mr. Ko. So the vertical asymptote would be when x equals to, I should not have used this. Let's change this like that. X equals to 0, because we can't divide by 0. Does anybody remember what the horizontal asymptote is? Y is equal to, remember if the denominator is bigger? As x gets bigger, 10, 100, 1,000, 1 million, what's 1 divided by a million? It is 0. So if you want to graph this, the graph looks like this. Sorry. So this graph is great and dandy, but in math, we want to find terms to describe what's going on with this situation. And by you just saying it goes to infinity, what goes to infinity? Does it go to infinity everywhere? Does it, like, how would you describe it? And in math, we want to find a common language, again, a common language that we can all agree to, that when we see it, it makes sense. Now, using limits to describe this, what does the graph look like as x starts its slow walk to infinity? As x gets closer to infinity, what does the y value look like? What does the function look like? And if you guys remember, this graph goes towards 0. The limit as x approaches 0, infinity of 1 over x, the answer is 0. Now, could we ever actually have proved it? Like, if you start plugging in numbers, if you plug in 10, 100, 1,000, 1 million, 1 trillion, 1 kajillion, 1 over the national debt of the United States, it wouldn't be 0. It would be a small decimal. And the point is that this allows us to rewrite it, to talk about it in a tangible way. If we could go to infinity, this answer would be 0. Will we ever get there? Nope. Because limits are not what it is, it's back to what should it look like. And I think that's an easy way of saying that. I don't have to definitely know that, hey, it's going to be here, but it's going to look like this eventually. Like, you guys will eventually look handsome and pretty. Not now, but if we go to infinity, you guys will look pretty one day. You guys will look handsome. It's okay. You'll get there. I shouldn't be recording this. So we can actually describe a lot of situations here. What would the limit be as x approach negative infinity? So now negative infinity is going to the left. See, x is going -1, -2, -3, -4. So what will the y value be? As this is crawling itself up from the depths of hell, it will get closer and closer and closer to 0. Some people will say -0. Let's go look for -0. 0 isn't positive or negative, so we just say 0. Some other characteristics of this, what would the limit look like as x approach 0? And remember, we have different sides. So we want to go from the left side, and we want to find out what the limit is from the right side, because they're not going to be the same. So looking here, as I approach 0, as I walk back to 0, look at the y value. Does the y value start approaching like an easy number like 1, 2, or 3? It starts shooting off. And let's look at that mathematically. If I write 1 over 0.1, 1 over 0.01. See, I'm getting closer to 0. 1 over 0.001. How many dimes are in a dollar? 10. How many pennies are in a dollar? 100. How many thousandths are in 1? That's 1,000. So as we get closer to 0, you can see the number is perpetually going to become bigger and bigger and bigger. So it's going to go to positive infinity. Will we ever get to infinity? Nope. Is infinity even a number? No, it's more like a concept. It's an idea. It will shoot off to infinity. So as vertical asymptotes that we talked about in pre-calc, you can never touch the vertical asymptote. You'll never be able to use it. But our question here is, hey, what would it have looked like? We can now describe the black hole. On the right side, oops, my bad. That's over here. Oops, I copied the wrong spot, guys. I was going from the right side. Those are positive numbers, so I've kind of flipped it. So let me erase this real quick. Got kind of excited. From the right side is the right section here. So that's the answer for the right side. That's over here. Sorry about that. That's positive infinity, right? So you shouldn't have to erase the answer. You could have just stuck a negative on it. So let's do this one over here. if I divide 1 divided by, that's approach 0, that's approach 0 now, approach 0 from the negative side, negative 0.1, 1 over negative 0.01, 1 over negative 0.001. Are you guys okay with the pattern? Getting closer to 0 from the left side. This becomes negative 10, negative 100, negative 1000. Does this look like it's going to positive infinity? It looks like it's becoming more negative. I'm becoming more in debt. Oops, sorry, miswrote that one. I was just talking. It becomes negative infinity. So we literally describe all the cases for this graph, either me going to infinity or me going toward the vertical asymptote. Now the follow-up question to this is, do we have a limit as x approaches 0? Now we talked about before, the idea of a limit is what should it look like? Now, if you go back and look at the graph, go back and look at this nice graph. Oops, erase that one. If we approach 0 from both sides, if you approach 0 from both sides, do you guys have a consensus of what it should look like at 0? Is there one point that they could both agree to? Isn't one going to positive infinity and one going to negative infinity? Are you going to go to heaven or are you going to go to hell? It looks like none. There's no limit. And the reason why there's no limit is because the left and the right limit do not agree. Do not agree. If your mom says we're having pizza tonight and your dad says I want McDonald's, you do not have an agreement. So guess what you're having for dinner? White rice. That's what happens at my house. Yeah, white rice. There's no limit. There is no agreement. And one of the cool things about if you do have a limit, you guarantee yourself to have an agreement. So, oh my gosh, we are almost out of time. These periods are so short. Okay, so a couple of takeaways are that, first, what is a limit? A limit is an idea of what should it look like, okay? What should it look like? And we're gonna learn various techniques to figure out what should it look like, whether an algebraic way or looking at a graph or using our left and right limits. A limit only exists if it's true from the left and the right side. They both are in agreement. Okay? The left side says 4, the right side says 3. They do not agree. No limit, no dinner. And we can use limits to describe certain situations. Like, what does something look like now at infinity? If I give you this dumb question here, limit as x approaches infinity of x squared, we all know what an x squared graph looks like. And if x got bigger and bigger and bigger, what do you think happens to the y? It goes to infinity. And that's a way that we can describe it now. We have a totally natural, quote unquote, natural way of describing that. But what does the graph look like as we approach 0? This isn't a funny graph. What does the graph look like if we're getting closer and closer to 0? Looks like 0, right? So limits oftentimes for 99% of limits are exactly what you think it should be. And that 1% is when it can go a little crazy. Okay. All right, I think today, since it was kind of short, we won't have homework. We'll start homework tomorrow when I see you guys tomorrow.